let's get some physics done. This is an Edexcel paper. It's physics triple. It's paper 1 and it's the higher tier, and it's 1 hour 45 minutes worth 100 marks. Now you can see here that I've already put all the answers in, so if you didn't want all the extra explanations to go with each answer, you can just skip each time I turn to a new page. Question 1. Sonar is an example of a use of ultrasound. State one other example of a use of ultrasound. Right, the typical uses are scanning for babies, so a baby scanner, cleaning jewellery, cleaning watches, cleaning glasses, things like that, cleaning rings, treating kidney stones, the vibrations from the ultrasound, smash them to pieces without having to operate on someone. Or a dog whistle, because ultrasound's above 20,000 hertz. Humans can't hear it, dogs can. Part B, state an example of a use of infrasound. The main one is studying the Earth's structure, all to do with seismic waves. Question C. Figure 1 shows the depth of the sea measured using sonar at different distances from the shore. A technician on a boat uses sonar pulses to measure the depth of the sea when the boat is 120 metres from the shore. Calculate the total time of travel for the sonar pulse used to make this measurement. The speed of the sonar pulse in seawater is 1,600 metres per second. So you can see here from the graph, when the person is 120 metres from the shore, so this is the distance from the shore, so when they're 120 metres, go down to the graph, read off from the graph, you can see that the depth of the sea is 14 metres at that point. Now with sonar, you're going to send the signal down, it's going to bounce off the seabed, and then the signal is going to come back up to the ship. So the total distance that the sonar is going to travel is 14 metres times by 2, so 28 metres. Use our standard equation, speed equals distance over time, rearrange that, so time is distance over speed. So that's 28 metres over a speed of 1,600 metres per second, and that will come out as 0.0175 seconds for that signal to go down and come back up again. Question 2. A student investigates what happens when light travels from air to glass. Figure 2 shows some of the apparatus used in the investigation. In Figure 2, angle Y is the angle of, well there's Y, and that's the angle of refraction. So that's D. If it asks you what this angle was, it's the angle of incidence, because it's the angle that's coming in. Part 2. Figure 3 is a graph of the student's results. Use the graph to calculate a value for angle Y divided by angle X. So you can pick any angle Y and its corresponding angle X. So I just took the angle of Y to be 14 degrees and the corresponding angle of X is 20 degrees. So 14 over 20 comes out as 0.7. The student concludes that angle Y is directly proportional to angle X. Explain what the student must do to test this conclusion in more detail. Right, they've only got a tiny little bit of data for that graph, so they need to gather more information or more data. Now remember, in the experiment, the person is changing angle X and they're trying to find out how that affects angle Y. So we need to use a wider range of angle X. And then once you've got that, repeat it. And take averages, you could say. Part B. The speed of light is that. The wavelength of yellow light is that. Calculate the frequency of yellow light. State the unit. Use this equation. So frequency equals speed over wavelength. There's the speed. There's the wavelength. Answer comes out as that. And the units, of course, for frequency is hertz. Question 3. Figure 4 shows a Geiger-Müller tube used for measuring radioactivity. Part A. Describe how a teacher should use a Geiger-Müller tube to compare the count rates from two different radioactive rocks. So this is a little tube here, and what you do is you put a little rock or whatever there, and if there's radiation coming off it, it goes down into the tube, and the tube can detect how much radiation's coming off. First of all though, before you measure the rock, you've got to measure the background radiation, and then place one rock at a set distance from the Geiger-Müller tube for a set amount of time and record the count. Subtract the background radiation count. So to work out the rock count, just say the rock count in the background was like 310 and the background was 10. So do 310 take away 10, so the rock count would be 300. Then remove that rock and repeat the above steps for the second rock. And once you've done that, do it again. Repeat the readings for both the rocks and take the averages. Part B. A hospital uses a radioactive isotope with a half-life of 6 hours. A technician measures a count rate of 80 counts per minute from this isotope. Complete the graph on figure 5 as accurately as possible to show how the count rate from this isotope will change from the time of the first measurement. The first point's already been drawn for you. So a half-life of 6 hours means every 6 hours, whatever the activity is, it's going to half. So at a time of 0, the activity is 80. So 6 hours later, it's going to half down to 40. And then another 6 hours later, so 12 hours, it's going to half from 40 down to 20. And then another 6 hours, so at 18 hours, it's going to half from 20 down to 10. Okay, and you always get a graph that comes down like this. It's an exponential shape. Part C. One radioactive source used in hospitals is technetium. Technetium is produced from the radioactive decay of molybdenum. Complete the following nuclear equation. Right, whatever this number is on the top, on the left-hand side of the arrow, when you add this number on the top to this number on the top on the right-hand side of the arrow, those two numbers have to equal that number. So something plus nothing had to equal 99, so that number there had to be 99. And the same for the number on the bottom. So whatever that number is there on the bottom on the left of the arrow, when you add that number to that number, it has to equal that number. So 43 plus minus 1 would give us 42. So the answer was 43. Question 4a. Which row of the table is correct for both force and velocity? So, well, both force and velocity are vectors. Remember, a scalar has size only, a vector has size and direction. So with a force, you've got to say how big it is, the size of it, and you've got to say in which directions it's pointing. We usually use an arrow. And the same thing for velocity. There'll usually be an arrow to show you which way it's going. So that's the direction and how big it is. So it'll have a number on it. Part B. Figure 6 shows a satellite orbiting the Earth. 1. State the name of the force that keeps the satellite in orbit around the Earth. It's the Centripetal Force. I've got a nice video all to do with centripetal forces. There's 3 types of centripetal forces. This one's gravitational. There's another one for tension, as if you were swinging something around your head that was on a string, like a hammer. And also friction, if there's a car going round in a circle, or going round a part of a circle when it's going round a corner. Part 2, draw an arrow on figure 6 to show the direction of the force acting on the satellite. That keeps the satellite in orbit around the Earth. Label this arrow F. So the arrow will be pointing inwards toward the Earth. If the satellite was over here, then the arrow would be pointing in this way towards the Earth. Part C. Satellites are used to gather data about the origin of the universe. The Big Bang Theory is a theory about the origin of the universe. Evidence for the Big Bang Theory is provided by redshift and cosmic microwave background radiation. Describe what is meant by redshift. So redshift is when the wavelength increases or shifts towards the red end of the spectrum. Red light has got the longest wavelength compared to all the other colours. So if you get something that moves toward the red end, then the wavelength's increasing. And when does that happen? It happens as the object is moving away from you. If the wavelength is increasing, it's almost as if the wavelength is stretching, and that's because it's moving away from you. If the object was moving towards you, that would be a blue shift, because blue is on the opposite end of the colour spectrum, where the wavelength's getting shorter. Part 2. Explain how redshift provides evidence for the Big Bang Theory. The Big Bang Theory states that everything started from a single point and expanded outwards or away from that point, and redshift is evidence of the galaxies moving away. Part 3. The Cosmic Background Explorer satellite observed cosmic microwave background radiation from 1989 to 1993. State what the M stands for. It's microwave. Part 4. State what is meant by cosmic background radiation. It's just radiation that comes from space due to the Big Bang explosion. Part 5. Explain how the presence of cosmic microwave background radiation provides evidence for the Big Bang Theory. So the Big Bang Theory involves a huge explosion that started the expansion of the universe, and cosmic microwave background radiation is evidence of the explosion. So remember, the whole theory is there was a huge explosion and then it expanded. So if they ask you what is the evidence of the expansion, well, that's the red shift. Question 5. Figure 7 shows a tuning fork. When the prongs of the tuning fork are struck, the prongs vibrate in the directions shown in the arrows on figure 7. Describe how the vibrating tuning fork causes a sound wave to travel through the air. You may add to the diagram if it helps your answer. So the vibrations are like that as the waves travelling like that. So sound waves are longitudinal, and with any longitudinal wave, the vibrations are parallel to the direction of travel of the wave. So parallel means it's in the same direction. Transverse would be perpendicular. They're the ones that go up and down. Part B. The following descriptions describe waves from different parts of the electromagnetic spectrum. Complete each description by adding the name of the wave. Use the name of each wave only once. Each description refers to a different part of the electromagnetic spectrum. So what I've done is I've underlined the triggers that allow me to identify the wave. Used in cooking, well, it could be infrared or microwaves. However, once they've said it's used for short-range communication, that's Bluetooth, not microwaves. So that would be infrared is what we use for Bluetooth. And it fits in with the typical wavelength as well. Description 2, used in cooking, so just like the first one. It's also used in communication, just like the first one. But the typical wavelength is 150 millimeters, so that's 15 centimeters. So microwaves are a few centimeters long, 1 centimeter long, 15 centimeters long, something like that. Description 3, so the third wave, again used in communication. Well, there's 4 waves that can be used in communication. It's all the 4 longest waves. And we've used 2 of the longest waves so far. It's produced by oscillations in electrical circuits. As soon as you see that statement, you know it's radio waves. And the wavelength, 150 meters, it's only radio waves that are that long. The 4th wave used in medical scanning, right? It could be gamma or X-rays. It's emitted by the nucleus of the atom. As soon as you see that statement, you know it's gamma. X-rays are formed from very high voltages. Part C. When white light crosses the boundary between air and glass, it can split up into the colours of the spectrum. Explain in terms of speed why the light behaves like this. Okay, well, different colours have got different wavelengths. If it's not in a vacuum, different wavelength light travels at different speeds. So they'll refract or bend by different amounts, causing the white light to split up into the colours of the spectrum, which is what we call dispersion. Question 6. The symbol G can be used to refer to the acceleration due to gravity. The acceleration due to gravity G has the units of meters per second squared. G can also have another unit. Which of these is also a unit for G? So what you do is think of an equation that's got G in it, gravity in it. Well, you've got weight equals mass times by gravity. Rearrange that equation so gravity is weight over mass. Right, what's the unit of weight? Well, it's a force, so it's newtons. What's the unit of mass? Kilograms. So newtons per kilogram is also a unit for gravity. Is it over here? Yes, it is. There it is. The answer was C. Part B. 2 students try to determine a value for G, the acceleration due to gravity. They measure the time t for a small steel ball to fall through a height h from rest. They measure t to be 0.74 seconds using a stopwatch. They measure h to be 2.5 metres using a metre rule. Calculate the value for G from the student's measurements. Use this equation. So you're not supposed to know this equation. It's just totally random. It's been made up or whatever. You just have to put the numbers in. So do 2 times by the height and divide that by the time squared. So the height was 2.5 metres and the time was 0.74 seconds. Remember to square it. I see so many students who forget to square it. And then that comes out as 9.13. Part 2. They record the time t for 2 more drops from the same height. The 3 values for time t are that, and that. Calculate the average value of time t to an appropriate number of significant figures. Right, well, they're all 2 significant figures, so we'll do ours to the same. So to get the average, just add the 3 numbers together, make sure you press equals, then divide by 3, and the answer will come out as that. And then let's take it down to 2 significant figures. Part C. Explain one way the students could improve their procedure to obtain a more accurate value for G. Use a computer or a data logger to record the time to eliminate human error due to reaction time. Okay, it's always the same answer for questions like that. Part D. A car travelling at 15 metres per second comes to rest in a distance of 14 metres when the brakes are applied. Calculate the deceleration of the car. Use an equation selected from the list of equations at the end of the paper. So what I do is identify what I've got. So that was the initial velocity. The final velocity is 0 because it's came to a rest. And they also give me a distance. Instead of putting D, I put X because I knew where this question was heading. And the deceleration, well, that's the same as acceleration, so that's A. So I'm looking for something with all of those quantities in. Now, if we zoom down to here, you can see the first equation is actually the equation we need. It's got the final velocity, the initial velocity, acceleration, and distance in it, so we'll have that. Right, so v squared minus u squared equals 2ax. Rearrange it. So you can see what I've done there. Put the numbers in, and the answer comes out as 8. If I go too fast, just pause the video. Question 7. Which of these is a non-renewable source of energy? Well, it's natural gas. Geothermal is from the hot rocks inside the earth. Tidal, as long as there is a moon, then there'll always be tidal energy. And solar, well, that comes from the sun. So again, that's not going anywhere anytime soon. Part B. Explain why renewable sources provide an increasing fraction of the electricity supply for many countries. This is a question where people don't understand what it means. Right, look, If the non-renewable sources like coal are running out, we're going to use them less. Now, we still want the same amount of electricity though, don't we? So that means that the renewable sources are going to get used more. So that's why they are the increasing fraction of the electricity supply. Part C. Electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1,300 joules of kinetic energy. Now, the kinetic energy of the water at the bottom, once it's fallen, will equal the gravitational potential energy it had at the top, assuming that we haven't lost any energy. So, the gravitational potential energy will be 1,300 joules. Now, the equation for gravitational potential energy is mass times by gravity times by height. Now, you're supposed to know that the gravitational field strength on Earth is 10 newtons per kilogram. So we've got gravity, we've got the mass, we've got the gravitational potential energy. Let's rearrange the equation to find the height. So I've rearranged the equation here, put the numbers in, answer comes out as 18.57. Part 2. As water enters the turbine at the bottom of the dam, the kinetic energy of 8 kilograms of moving water is 1,100 joules. Calculate the speed of the moving water as it enters the turbine. So kinetic energy is a half mv squared. But if I know I'm rearranging it, I will write the equation as kinetic energy equals mv squared over 2. Now let's rearrange that. So you can see I've just multiplied both sides by 2 to give me this. And then I've just rearranged for the m. Now, I don't want v squared, I want v. So if I square root both sides, that will turn v squared into v. And that'll equal the square root of 2 times by the kinetic energy divided by the mass. So this is a common rearrangement. Because it's tricky, they use it quite often. So make sure you learn how to do it. Put the numbers in, comes out as 16.58. I've just rounded it up to 17. Part D. Moving air can be used to generate electricity using a wind turbine. Figure 8 is a graph of kinetic energy against wind speed for a mass of moving air. Just before the air reaches a wind turbine, it has a wind speed of 15 meters per second. When the air has gone through the turbine, it has a wind speed of 13 meters per second. As the air moves through the turbine, some of its kinetic energy is transferred to the turbine. Yeah, we know that because the wind is slowed down. Use the graph to determine the percentage of the kinetic energy transferred to the turbine from the air. So the initial speed, 15, using this graph, that tells us that the kinetic energy of that air is 5.2 kilojoules. Now, after it's been through the turbine, the final speed is 13. So once again, if we look at this graph, get the wind speed for 13, that means that that air had an energy of 3.9 kilojoules. So the kinetic energy that's being transferred to the turbine will equal the kinetic energy lost by the wind. So that will equal the kinetic energy that the wind had when it was travelling at 15 meters per second, take away the kinetic energy that the wind had when it travelled at 13 meters per second when it came out the other side of the turbine. So that value in kilojoules, take away that value. So they've lost 1.3 kilojoules worth of energy to the turbine. Now, we need to work out the percentage of the kinetic energy transferred to the turbine. And the way we do that is divide it by how much initial kinetic energy it had and multiply by 100 to get it into a percentage. So that's how much energy has been transferred to the turbine. That's how much energy the wind had at first when it was travelling at 15 meters per second, multiplied by 100. So it turns out that 25% of the energy was transferred from that wind to the turbine. Question 8a. A student investigates how different surfaces radiate energy as they cool. Figure 9 shows some of the apparatus used in a part of the investigation. So I've got a copper container here and some hot water. Describe how the student could collect data to show how the rate of cooling of the container and water change with time. Okay, well, use a thermometer to measure the temperature and a stop clock to measure the time, and basically measure the temperature at regular intervals as the water is cooling, and that'll tell you the rate of cooling. Instead of saying use a thermometer and a stop clock, you could say use a data logger, which has got both of those things in. Part B. Figure 10 is a graph of intensity against wavelength for the electromagnetic radiation emitted by a halogen lamp. Describe how the intensity of the radiation varies with wavelength. Okay, so looking at this, you can see the visible light, the wavelength's getting bigger, intensity is like that. So as the wavelength gets bigger at first, the intensity is increasing till it gets to a certain peak, and then as the wavelength continues to increase, the intensity drops. And that's what I've wrote there. And it's a non-linear relationship between intensity and wavelength, because it's not just going upwards as a straight line from bottom left up to top right. Part C. Figure 11 is a graph of temperature against time for a halogen lamp for the first 120 milliseconds after it's been switched on. Calculate the gradient of the graph at a time of 30 milliseconds, state the unit. So that's the time along the bottom, that's the temperature up here. So calculate the gradient of the graph. So we need to draw a tangent. I've drawn that in orange. So a tangent is a straight line that hits the graph at the point when you want to know what's happening. So we can see at this point here, that orange line represents what the graph's doing. Okay, approximately. They'll always accept a range of answers. And if you show you're working out, they'll always be lenient as well. So we can see this line. You can draw that line as long as you want because it's straight. So the gradient will be constant. Now, just stop drawing the line down, the orange, at a point that's convenient. So I stopped it there, which was nicely on 180 degrees. And I kept on drawing the line upwards until I got to 270 degrees. So you can see that the change in the y-axis, okay, dy means change in y-axis, and temperatures on the y-axis. So the change in the temperature is 90 degrees C. Now we need to find out what the change in the x-axis was. So again, I'll conveniently stop drawing this orange line at that point there, which was on 12. And I stopped on that point there, so not in between the squares, like on the square itself, and that came down to 48. So this is a change of 12 to 48, which is 36, and the unit is milliseconds. So to get the gradient, you do dy by dx, so that's the change in the y-axis divided by the change in the x-axis. And in this case, that equals 90 degrees C divided by 36 milliseconds, which came out as 2.5. And they want the units. That's why make sure you put the units in here. So it'll just be degrees C's divided by milliseconds. Degrees C's per millisecond. Part 2. Explain why the temperature of the lamp rises and then remains at a constant value. Well, it's the same as anything whose temperature rises. The temperature rise is due to more energy being absorbed by that object than is being emitted by the object. Energy in is greater than energy out. And then, why does it remain at a constant temperature value? Well, it's always the same. Constant temperature is due to the energy being absorbed being equal to the energy being emitted. So in other words, energy in equals the energy out. Question 9. The student investigates the relationship between force and acceleration for a trolley on a runway. Figure 12 shows some of the apparatus the student uses. Describe how the student could increase the accelerating force applied to the trolley. So the thing that's going to make the trolley accelerate is how much weight is on that hanger. Because you drop that hanger and it's going to pull the trolley across to the side. So basically add more weight onto the hanger. Part 2. Describe how the mass of the moving system can be kept constant. Now this is a question that always confuses students, and I think the examiners have got it wrong here. There's usually a mass, some kind of masses on the trolley. And a moving system just means the parts that's moving. So the trolley's moving, the card's moving, and this weight hanger is also moving. So to keep the mass of the moving system constant, whatever mass or weight you put onto this hanger, it should come off of the car. Okay, it should come off the trolley. So transfer the mass from the trolley onto the hanger. It's easy once you know how to answer it. Part 3. Explain how the student could improve the procedure to compensate for the effects of frictional forces acting on the trolley. What you want to do is detach the weight hanger, raise the runway so the trolley just starts to roll, because this will reduce the effect of friction, trying to stop the trolley from rolling, and then obviously reattach the weight hanger when you're ready to start the experiment. And I've done a little picture there. Part B. Figure 13 shows two objects, Q and R, before and after they collide. So before, Q is moving, R is not. Then there's going to be some kind of impact, and then after, they're both moving. The arrows show the direction of movement of the objects. The arrows are not to scale. Explain how momentum is conserved in the collision. Well, that basically just means the momentum at the start equals the momentum at the end. Use Newton's third law and Newton's second law in your answer. And it's saying Newton's second law can be written as this. Change in momentum over time is the force. Normally it says force equals mass times by acceleration. Right, let's start with the basics. Momentum is going to be conserved. So how do you calculate momentum? Well, momentum is mass times by velocity. Now, if we use Newton's third law, it states for every action there is an equal and opposite reaction. We'll get a mark for that. And so when Q and R collide, the force of R on Q, so at this point here, is going to equal the force of Q on R. However, I've put a negative sign in there because the directions are going to be opposite. So Q, the force of Q on R is going to be to the right, and the force of R on Q is going to be to the left. So it's going to be the same size, but opposite in direction. That's what Newton's third law states. And we show the opposite in direction by the negative sign. So this force here, well, we could say that force there, well, look here. The force equals the change in momentum over the time, doesn't it? All right. You'll often see it as impact force, and that time is the time taken for the impact or the collision to happen. So we can take this force and we can put in change of momentum of Q over time. All right. So take that force out and put change of momentum over time. And this one over here, the force of Q on R, will now be the change in the momentum of R over time. Now, because the time taken for the collision is the same, you know, when Q bumps into R, that might be 1/10 of a second, and that means that when R is bumping into Q, that's also 1/10 of a second. So we can get rid of the time, which just leaves us with change in momentum of Q is going to equal the negative change of momentum of R. So therefore, the momentum lost by Q has been gained by R. So the momentum has been conserved. In other words, the momentum at the start equals the momentum at the end. And you can see from the picture here, Q is obviously going to have to lose some of its momentum because R has gained some momentum at the end. Part 10. Fusion and fission are nuclear reactions in which large amounts of energy is released. In a fusion reaction, two hydrogen nuclei are forced together to form a helium nucleus. Explain why a very high temperature is needed for this reaction to happen. Right, the two hydrogen nuclei will both have the same charge, so they'll repel each other. Now, we need a very high temperature is needed, so the nuclei have very high energy and a very high speed to create an impact force that'll be large enough to overcome the force of repulsion. Okay, these two things, these two hydrogen nuclei are not going to want to join together. We're going to have to force them together. So we're going to have to smash them at very high speeds into each other to overcome the repulsion. Part 2. In a fusion reaction, the combined mass of the two small nuclei is greater than the mass of the resultant nucleus. This decrease in mass m appears as energy E according to the equation E equals mc squared. So that's Einstein's most famous equation. C is the speed of light, which is that. The energy released in one fusion reaction is that many joules. Can you calculate the decrease in mass? So we'll just take E equals mc squared and rearrange it to find what mass is. So that's going to be E over c squared. Pop the numbers in, make sure you square the speed of light, and it comes out as that. And again, people often forget to square the speed of light. Part B. Nuclear fission is used in nuclear reactors in some power stations. In the reactor, a fission chain reaction is maintained and controlled to produce a supply of energy to generate electricity. Figure 14 is a diagram of a nuclear reactor. So it's got some movable rods, there's some shielding in there, coolant, nuclear fuel, graphite core, reactor vessel, and there's some coolant going in. Explain how the graphite core and the movable rods are used to maintain and control the chain reaction. Right, well, nuclear fission releases neutrons. I've drew a little picture down here, right? What you do is you take a neutron, you bash it into a large unstable nucleus. That large nucleus becomes smaller. You get two smaller nuclei, two smaller nucleuses. You get more neutrons being released, more neutrons, which can initiate further fission reactions, and that's what causing the chain reactions. Plus you get some energy released. That's what we want. We want that energy. So we can use that heat energy to heat water, turn it into steam, and use the steam to turn a turbine to create electricity. Anyway, and then these neutrons can go on to hit into more large unstable nucleus. Okay. Right, so some of the neutrons are too fast. So some of these are too fast to be used to initiate further fission reactions. So the graphite core is a moderator which slows down the neutrons so they can be used for fission. If the chain reaction becomes too fast, the movable control rods, which are usually boron if you get asked, can be lowered to slow down the reaction. So you lower these rods down, and that slows or completely stops the reaction if you put them right down. Now, how do they do that? Well, by absorbing neutrons. So the neutrons are not available to initiate further fission. Alright, and it looks like that's the end of the paper. Let's always double check. Yes, it is. Okay, so I've absolutely bashed that one. And I hope those explanations are going to help you for your mocks and for your future summer exams. Please subscribe to the channel if you haven't already. Like the video, it helps us out a bunch. Work hard, be nice, and I'll see you in the next video. Bye for now.